recording. Alrighty. So we were talking about propositional logic. We talked about quantifiers on Wednesday, and we're going to spend today continuing to talk about quantifiers. And just as a very brief reminder, right, if we have something like all x in some domain D, Px, right, this just means Px is true for every or all x in the domain D. And then we have this funny backwards E thing that means there exists at least one thing for which it's true, right? So Px is true for at least one x in D, okay? And we ended with, we were doing some examples, and I wanted to start today just by doing a bunch of examples, especially examples where we have kind of multiple quantifiers, because one of the last examples we did on Wednesday was that, and it's confusing. It's genuinely can be a little hard to wrap your head around until you get used to it. So I'm going to write 4 or 5 examples up, and I want you to talk to some people around you and see if you can agree on which of these are true and which are not true, okay? So, natural numbers n, this is less than C. I'm gonna leave a little so we can leave a little space so we can maybe write something. All right, so go ahead and start chatting about these while I'm writing these up.
First one.
Do you have that?
Because you're just messing right there.
Oh, there we go. Okay, just making sure I'm not in the way.
At least one MZ is bigger than at least for every natural number in the domain of truth for at least one in Z. That's bigger than Z. I mean that. It's just comparing two numbers that's I believe that's true. There's going to be a number that's bigger than another number.
Oh, wait, you know, because the rules break me that you said that.
Yeah.
And then we have
Okay. Because these all integers in any
All
oh, yeah. In the domain of the natural number.
that's the same logic.
It's just the inverse. Except it's all natural.
But this logic
And so you can't.
So no.
I guess they're saying that every Z is going to be bigger than the number natural number. Oh, I was looking at 3, yeah.
Okay, I'm sorry.
3 is definitely false. 4.
So yeah.
2 is the inverse of 1, so that's also true. If you think about it, it's literally just flipped.
It would
have to be and then 3 I said was false because it's from what I see it's saying that no matter what n you pick, Z is always going to be bigger. Every Z will be bigger than n. Even I just don't think
because you put it. See, that's
Okay.
Ready to talk about these, or you want a few?
Release one and domain n. All z's.
Ready?
Okay. So all
right.
z's.
So for the first one, let's vote. So you are required to vote. You may not just like be like, I'm not sure, I'm not gonna raise my hand, okay? But it's not part of your grade, so don't worry. How many people think number 1 is true? Raise your hand. How many people think it's false? Okay, let me see what I think. So what does this say? This says, for every natural number n, there exists some integer z such that n is less than z. So someone who said that's true, why do you say that's true? Yeah, Connor?
You're just comparing two number sets. You can always pick a number that's going to be bigger than any number that's in a set technically, because they're both infinite.
Okay, yeah, so you're saying, look, no matter what number you pick here, or no matter what number you're thinking of here, you can always pick some integer that's bigger than it. Yeah, I agree. Good. So, true. Maybe I'll write a little, right? For every n, there will always be some z bigger than it. Right, but one important point to note, and so hopefully we talked about this last time, and it seems like this didn't trip anyone up, but right, for each n, we get to pick a different z, right? Because this would not be true if you had to pick one z that had to work for everything, right? Okay. How about number 2? Let's vote. How many people say true? How many people say false? Okay. So what do you think? Why is this true? Someone else. Spencer?
Same reason, you can always just pick a number that's larger than
Same reason. Okay. So what's different between these two?
is that the set is integers. For all integers, there exists a natural number that's larger than,
Okay. And why doesn't that make a difference?
because larger than is on the positive side of the,
Okay, I see. Right. So you're saying, well, this could include negative numbers, but if you have a negative number, well, fine. You can just pick 0. It doesn't matter. Like, you can always still pick a positive number that's bigger than. Yeah, I agree. True. Okay. How about number 3? What do you think? True or false? Should we vote? True. How many people say true? How many people say false? Everyone says false. So for all integers, there exists a natural number that is smaller than it. Okay, why is that false? Maggie?
It's because the integers, they account for the negative numbers and the positive numbers, but there's not going to be a case where a natural number is less than, like, let's say, like a negative integer. So it
Right.
must be false.
Yeah, and so and it was good when you said, oh, say for example, right? If you're trying to say that a for all is false, then the way to do that is to say, here's an example where it doesn't work, right? So you said, like, I don't know, -5. If you choose z to be -5, you can't pick a natural number that's less than it. So false. In g, when z is -5.
That's true.
No natural number is smaller.
But if z is the set number,
You can pick a net. You can pick no, because z is infinite. It's all. And you can pick one and make it the lowest end.
z the negative.
Number 4? True, false, what do you think? I heard
That's
false.
right. It is. It's definitely false. And my first right was.
So what does this say? There exists a natural number. So this one, let's see. Oh, no, it's not quite the same. Okay. There exists a natural number such that all integers are bigger than it. So why is that false?
Just pick n equals 0 and z is any negative number.
Pick n equals 0 and then what?
Z is any negative number.
Okay, so that, I agree that doesn't work, but we can't just, so, to say why an exists is false. It's not enough to just say, well, here's an example where it doesn't work. Right? Because it's enough for it to work for just one number. So you have to somehow argue why it won't work no matter what number you pick. Right? So like, so Spencer just said, yeah, well, it doesn't work for when n is 0 because like, you know, it's not true that all integers are bigger than 0 because like there's negative numbers too. Right? So, but why is it true that there are no natural numbers that would work? Yeah, Connor?
The problem is that you have two infinite, I mean, from the point of n being smaller than z, you have two infinite data sets. And so you can't really just pick an n that's going to be always smaller than a z, and because of that fact.
Okay. Yeah. Yeah, you're right. I mean, so you're right. It is. This is indeed false. I was just pointing out that it's not quite enough to just say, well, for example, it doesn't work for 0. You have to say, no matter what natural number you wanted to pick here, it's not going to be like that natural number will not be smaller than every integer. So this is false. Okay, how about the last one? How many people say true? How many people say false? Some people didn't vote. Let's try again. How many people say true? How many people say, anyone say think it's false? Okay, why is it true? So, to say that this doesn't exist, so to say this is true, you have to tell me a specific number. Maggie, what number do you want to pick?
Oh, I was just gonna generalize it.
Oh, okay.
So whenever you're saying that the natural numbers are greater, all you have to do is just pick a negative integer. and then
Okay,
that's-
so you want to say pick a negative integer here.
Yeah,
So what integer do you want to pick?
-13.
Negative 13, okay, good choice. So then, is it true that all natural numbers, that negative 13 is less than all natural numbers? Yeah, it is. True. Z equals negative 13. Okay, good. What questions do you have about those? Brayden?
So does that E symbol that we're using
Hmm?
next to the upside down A, is that supposed to mean like there exists?
Yes, the backwards E means there exists.
A type of variable compared to for all this variable?
Maybe I'm not sure I understood your question. So you're
So the
asking?
variable is like integers, like there exists an integer,
Mhm.
and we're comparing it to all of the natural numbers.
Well, right. We're comparing it because we're using a less than.
And so you can have a number that, you can have an integer that exists that's less than the natural number.
Right. This says there exists an integer such that this is true. And what this says is every natural number is greater than that integer. Right. So they're nested, right? I think I maybe drew this the other day, but
That's what it is. I was-
you have to, so if it helps you, you can draw in the extra parentheses. And once you get used to it, you probably don't need them, but it can be helpful to remember that it really is like this, right? The very first thing says there exists an integer such that what? The such that what is everything else.
And you can choose the number,
What was that?
and you choose the integer for the there exists part.
This here?
Yeah.
This can be whatever, it can be any domain, yeah. It doesn't have to be integers.
Oh. No,
Yeah, I mean, here-
I meant like, because it's written as an integer.
Mhm.
I was saying like, you put the existential quantifier,
Mhm.
and it's like you can pick whatever the number's going to be, the existential quantifier, to see, and then compare it to, for all in the domain of n.
Mhm. Yeah, we can pick this to be whatever integer we want. Is that what you're
Yeah.
asking? Yeah.
Yeah, that's what I was asking.
All right. I'm going to do a few examples going the other direction. So I'm going to write down a few sentences in English, kind of mathy sentences in English. And I would like you to talk to your neighbors and see if you can write down, you just, get out some paper if you don't have paper out, or just in your head, but like how would you write this down formally in propositional logic using things like for all, there exists, and other stuff that we know. You could use and, or, whatever. Does that make sense? Maybe we'll do one example all together, and then I'll write down some more that you can do. So here's the first example. Every natural number is less than or equal to its own square. Okay? So I'll kind of do this one to show you what kind of thing I'm asking you to do, and then I'll give you some more examples. So first of all, I look at this and I say, this word every, that's a giveaway that we're talking about some kind of for all, right? So words like every, each, all, and every what? Every natural number, okay? And so it's going to be something like for all, some variable in the domain of natural numbers. This statement doesn't mention any variable names because we don't typically talk in terms of variables in English, right? But we can make up whatever name we want. It doesn't matter. N is a nice one to choose if you're talking about natural numbers, but it really could be anything you want. It doesn't even have to be a single letter. You could say for all monkey natural number, whatever. Okay, and then what? What is true about that number? Is less than or equal to its own square. So I can just say n is less than or equal to its own square would be n squared. Okay, so that's how I would write that formally. Does that make sense? Any questions about that? All right, let me write down some other sentences and talk to your neighbors and see if you can decide how you would write these formally. So this one is the square of any integer is non-negative. 1369 is a perfect square. All right, go ahead and chat about these with your neighbor. Take a minute or two.
I just did. It's not even actually.
I will say one thing as you start on this. So this one like uses the word any, and so you're like, this is probably some kind of for all, right? These ones are a little bit sneakier. So I promise that there is a nice way to write each of these that uses something like a for all or it exists, but it's not as obvious, right? There's not like a single word there that's going to tell you what it is. So you're going to think a little harder. Go ahead.
We also have to make sure it's not negative, but it's also easy. So this function showing it's not
Perfect square. All of these would be one line, right?
I mean, you can write anything in one line if it's long enough.
Yeah, that's true.
But yes, you should be able to write these in one line, yes.
like it's greater than negative 1, so we can do like the non-function with the integer less than 0.
Is a defined is something that is you can square root and return a non-decimal value. Oh wait, it will return a non-decimal value. So that means it just won't be for if you
Thirteen
1369.
This will be either natural.
Oh yeah. For all 1369.
I think it could be could be like a natural number, and then what we do with the function is like
It could be like
modulus division. Does that count?
like saying for all 1369. A perfect
We're trying to
square.
find out if there's no decimal place, right? Could be something like there exists like an actual number of integers in which the function is
Does not.
let's say
Well, I mean, technically, so it does not. That's true. You could say that. There's this in the integer square.
That should be there exists.
All right. I don't think everyone's made it through all of them. That's okay. I hear lots of muttering about number 3, which is great. So let's do number 2. Someone want to volunteer? How would you write this? The square of any integer is non-negative. Yeah, Maggie?
For all z and integers, you said z squared is greater than or equal to 0.
Z squared is greater than or equal to 0. What do y'all think? Seem good? Yeah, I agree. This is great. Right, so that any integer, we're talking about for all integers, and then something being the square of something being non-negative, right? It says if you square it, you get something that is greater than or equal to 0. By the way, is this true or false? Is this a true or false proposition? It is in fact true, yeah. But we can perfectly well encode it in formal logic whether it's true or false, right? That's not the point of this. But it is also a nice exercise to think about whether they're true. Okay, how about number 3? Anyone come up with a way to write number 3? Yeah, Sanskriti?
There exists an element s in an integer where s squared equals 1069.
There exists an integer s such that you said s
Yeah.
squared
S squared
equals 1,369?
Mm-hmm.
Yeah, great, very good. I think I heard you all talking about this too. The thing that I also heard some people talking about, which is what everyone thinks of first, is like, well, if you take the square root, you'll get something that doesn't have anything after the decimal point. You could also write it that way, right? You could say something like, the square root of 1369, but like you need some predicate that means it is an integer. But like, okay, so first of all, square root is really complicated. Like even defining what square root means, we're all used to square root, right? But if you really think like, if someone didn't know what square root was, how would you define it? Well, you would define it by something like this. You would say, well, square root is the number that, when you square it. But so like how you actually compute it is complicated. Calculators can do it for you. But if I just gave you a number and I'm like, yeah, just using pencil and paper, what's the square root of this? You'd be like, I don't know. Also, saying that something is an integer, we haven't even, so like square root would return some kind of like real number. We haven't even talked about real numbers, right? And we're really not going to use them in this class. But this is a much, in some ways it seems like thinking about taking the square root and checking that it's an integer is backwards, right? Instead of thinking about that, we should say, no. Something being a perfect square means it is the square of something. And so we can directly say there exists that something that when you square it, you get 1369. Right? The only concepts we need to say this are, we need to know what it means to square something, just multiplication, right? And for two things to be equal and exist. That's it. We don't need to talk about real numbers, square roots, any of that complicated stuff. So, very good. Did anyone get to number 4? Yeah, Jack, what do you think?
There exists an integer z such that n divided by 2 equals z.
Such that n divided by 2 equals z. What do y'all think? I think there's a slightly, so this is good. This is correct. There's a slightly simpler way to write it, though, I would say.
Do we have a modulo equivalent?
What was that?
Do we have an equivalent to modulo?
Not yet. We're going to talk about that later in the semester, but yeah. We don't need that. There's a simpler way to do it. Spencer?
N over 2 is an element of natural numbers.
N over 2. Yeah, that's not really simple. I mean, saying something is an element of the natural numbers is, it's basically saying there exists a natural number that is equal to that, right? Anyone else? Yeah, Maggie?
Is it just 2n?
2, say that again?
Is it just 2, like 2n?
2n? Like, what do you...
I didn't really think about the other side, but I guess like if you have 2 negative
I'll leave
numbers,
yours.
or 2 odd numbers.
So, I think you're on the right track. What does it mean for something to be even?
It's divisible by 2.
What was that? It's divisible by 2. Yeah, and that's what this says, right? How else could you say that? It's a multiple of 2, right? We think of those as meaning the same thing, but they're actually slightly different. So how would you say formally that something is a multiple of 2?
It's multiplicative inverse.
No, that's way too complicated. Much simpler. Yeah, Jack.
Yeah, there's an integer z such that n times z equals n. Or no, sorry, 2 times z equals.
Yes, there is an integer z such that 2 times z equals n. Yeah. Yeah. So this says like n is divisible by 2. Divisible by 2. And this says, n is a multiple of 2. Right? Anyone want to guess why I think this one is simpler than this one? They are kind of equivalent, right? But I think this one is actually simpler. Why do you think I would say that? Yeah, Connor?
Because n is put into the calculation in the first one, whereas n is the result of the second one.
That's a good guess. That's not really why I would say this. I can kind of do calculations with, ultimately I'm doing some calculations with some things, and I think it really makes a big difference what's the result versus what goes into it. Yeah? Spencer?
Multiplication is easier than division.
Multiplication is easier than division. Why?
Because division is defined by multiplication.
Division, yeah. Typically we define division in terms of multiplication. Yeah. Yeah, and also, if you want to talk about division, you need something like the rational numbers or something, right? But multiplication we can define just in terms of natural numbers or integers. And so multiplication is a kind of fundamentally simpler operation than division. And so if we can just talk in terms of multiplication, right? This statement just lives entirely in integers. For this statement to make sense, you have to have some idea of what division by 2 means. You have to think in terms of the rational numbers. And so it makes it a little more complicated. Yeah. So I like this one. I want to emphasize though, this top one is correct, right? It means the right thing, but if we're going to then work with it later, it's easier. We make things easier on ourselves if we use this version. Okay. This is going to come up a lot. We're going to use this many examples. So I'm basically going to define for an integer n, we're going to define the predicate even n is defined to be that there exists, I'm going to say, an integer k such that 2k equals n. Right, that's going to be our definition of what it means to be even. By the way, so how would you then say, here's another example, how would you say n is odd? There's a couple different ways to do it. Yeah, Spencer.
Does not equal instead of equal.
So,
Or
what exactly would you say?
like put a negation in front of it. Like put a.
Oh, just say not even? Well, yeah, well, okay. Where would you put the negation? This is important.
There does not exist.
There does, okay, so you want to say not even n, which is the same thing as saying, like if we expand it out, there does not exist. Yeah, so there does not exist k such that 2k equals n, or an integer k. Yeah, what's a different way we could define it? So this is defining it by saying what it is not. Is there like a more direct positive way that we could say what it means to be odd?
2k equals n plus 1.
Yeah, so we could also say there exists some integer k such that n equals 2k plus 1. So it's n is 1 more than some multiple of 2. Right? These two definitions turn out to be logically equivalent, as we all know, but we won't be able to prove that until a few weeks from now. It's surprisingly tricky to show that these mean exactly the same thing, because it depends on the fact that basically these are the only two options. If you have a number, it's either going to be a multiple of 2 or it's going to be one more than a multiple of 2. But that's not like, it's not immediately obvious why that would be true. Okay. Questions? I'm gonna show you one more example kind of quickly, and I'll just tell you instead of having you think about it. But if n is even, then n plus 2 is even. Okay, so this has an if-then, so we're going to use some kind of implication. The tricky thing about this one, and so you might just write down, like now that we've defined this predicate even n, we can just reuse that. I could say even n implies even n plus 2, right? I would say this is not quite complete though. Because typically in math, when you make a statement like this that just mentions a variable, it's implicitly saying this is true no matter what value that variable has. So there's really a for all hiding in there, even though it doesn't say for any n, if n is even, then blah, blah, blah. But just the fact that it mentions this variable and doesn't give you context about what it is, means implicitly we're making a claim that no matter what you stick in for n, it's going to be true. So really, I would argue the correct way to encode this would be to say, maybe like for all integers n. That's just something to watch out for. That sometimes there's a for all hiding, even though that word doesn't occur. Okay. All right, one more thing I want to tell you about, and then we'll do our quiz. And this is something that we've kind of been implicitly using a few times, and you may already have an idea about this, but I want to write it down explicitly. De Morgan laws for quantifiers. So, what is the negation of a for all? So if I say for all x in some domain, p of x, what's another way I could write that? What does it mean if it is not the case? Let me move this over a little bit. That p is true for all x in this domain.
P is just like there exists an x in the domain.
There exists an x in the domain such that what? Such that p of x? What do you think? Is it not p of x? What do y'all think? Which is it? Not? Connor? What are you going to say? No? Okay. Yeah, there should be a not. Right? Intuitively, there's a couple ways to think about this. So one, you can kind of think of it on an intuitive level. If it is not true, if p is not true for every single x, then there must exist at least one x where p is false. Right? And that's what that says. You can also think of it, right? Remember that this is kind of like a big and, px1 and px2 and px3 and dot dot dot. Right? And what happens when we put a not on an and? Right? We have that De Morgan law that says we can push the not inside, we have to flip all the ands to or. So this is going to be like not px1, oops, or not px2, or not px3, or dot dot dot. Right? And that, and a big or like that, that's just an exists. I don't know if I said that the other day. Did I? I don't remember. But hopefully that's clear, right? A for all corresponds to a big and, means they all have to be true, and an exists corresponds to a big or. At least one thing has to be true. Okay, and what about if we say not exists? There does not exist x such that px is true. What's another way I could say that? Brayden?
Would it be like for all in this domain, the x would be true?
Like that?
Yeah. Wait. No, should it have not the x?
What do y'all think? Should it have a not there? If there does not exist an x such that px is true, then yeah, that means for every single x, px is false. And again, you can, if you think of it expanding out the exist as a big or, and you put a not on it, it's gonna, all the things will have a not and it'll all flip to and. Right, so for all and exists are dual to each other in exactly the same way that and or are dual to each other. Which is why we call these De Morgan laws also, because it actually is kind of the same thing if you squint hard enough. Questions? questions do you have? So, right, you should know these. You can kind of, like, we made those big table of like laws for propositional logic, for like algebraic laws for propositional logic, right? These two should go kind of with that whole table of laws also, because these are two of the most important laws for manipulating. If you have things that involve quantifiers, right, these are really nice, because we often will write down some statement that involves for all, exists, or whatever, but then you'll see many examples of this where we want to know, okay, what is the opposite of this? What is like the negation of this? And it's really helpful to be able to just keep pushing the knot all the way down until it's hard for as humans to think about the negation of a complicated thing, right? So we can take the negation of a complicated thing and turn it into a more positive statement that only has knots kind of at the very bottom level. And that's easier for us to think about. And so this is going to let us do that algebraically without having to think hard about it. We can just write down some symbols and kind of figure out the answer. Okay. There's an example of that, but if you look in the lecture notes, you can see that, or there'll be examples in the homework. All right, let's do our quiz. So just remember, as a brief reminder, right, there's two problems in the quiz. This first question is learning goal 1. The second one is learning goal 2. You can do both, either, neither, whatever you feel prepared and comfortable doing. If you get credit for them, fantastic. You now have credit for those learning goals. If you do not, then you'll have another chance. You know, these learning goals will still be on the quiz like for the next few weeks. You can also always come to office hours. So